Today, we're diving into a really cool AI breakthrough called Prism. It's all about tackling one of the single biggest headaches for large language models. How in the world do you get them to read huge amounts of information, like super fast, without missing any of the important stuff? I mean, just think about it for a second. What if you could feed an AI an entire novel, or a really complex code base, or maybe even a feature-length film, and it just got it instantly? This has been the holy grail for AI for a long time, but there's always been this fundamental wall standing in the way. Well, that might be about to change. So what is this wall? Well, it all boils down to a problem we could call AI's attention deficit. You see, even our most powerful, most sophisticated models today start to choke when you give them too much information at once. Now, the magic sauce behind how these models understand language is a mechanism called self-attention. It's brilliant, really. It lets the AI look at every single word in a sentence and figure out how it relates to every other word. It's what gives AI that deep, contextual understanding. But, and this is a huge but, this incredible power comes at a very steep price. Here's the kicker. The computational cost for self-attention doesn't grow in a straight line. It's quadratic. That means if you double the length of the text you give it, you don't just double the work, you quadruple it. And this visual just says it all, doesn't it? As the amount of information, what we call the sequence length, goes up, the cost just explodes. It goes vertical. This is what makes processing long things, like a whole book, incredibly slow and ridiculously expensive. It has been the biggest bottleneck holding AI back. So, faced with this computational brick wall, researchers everywhere started hunting for a shortcut. I mean, there had to be a smarter way to do this, right? The AI couldn't possibly need to look at every single word all the time. And this led to a really clever idea called block sparse attention. The logic was pretty simple. What if, instead of analyzing every single word-to-word connection, the AI could just look at bigger chunks or blocks of text and just figure out which blocks are most relevant to each other? And to make that happen, they used a trick called mean pooling. You can think of it like asking the AI to write a super quick summary. For each block of text, it just kind of averages out all the information to get one single data point that represents the gist of it. It's a fast way to get the vibe of a paragraph without reading every single word. But here's where the mystery starts. This shortcut, it wasn't working right. Yeah, the AI was faster, for sure, but it was also dumber. It was missing key details, it was getting confused about the local context and the fine-grained relationships between words. The shortcut had a secret hidden flaw, and for a while, nobody knew what it was. And this is where the researchers behind Prism had their big aha moment. See, they didn't just try to patch up the shortcut. They dug way deeper to find the actual theoretical root cause of the whole problem. And here it is, a quote straight from their paper. They figured out that the problem wasn't really with mean pooling by itself. The problem was how it was interacting with another system called rotary positional embeddings, or ROPE for short. ROPE is basically what tells the AI where each word is in a sentence. And these two systems, they were clashing. Big time. Okay, now this part is fascinating. Stick with me. This slide shows what the AI is seeing. ROPE creates two different kinds of signals. On the left, you've got the low-frequency signals. Think of these as the big picture vibe, the overall meaning. Like, these paragraphs are both about the same topic. Then on the right, you have high-frequency signals. These are the nitty-gritty details, the precise word order, the grammar, and AI needs both of these to really get it. And here is the core discovery. Mean pooling, that summarization trick we talked about, was acting like a low-pass filter. It was doing a great job of preserving the big-picture, low-frequency signals, but it was accidentally and completely wiping out the crucial high-frequency signals that held all the details. So this created what the researchers called a blind spot. In the dead zone, all those high-frequency positional details were just gone. Poof. In the transition zone, the signal was there, but it was super weak and garbled. Only in the semantic zone, with the big-picture stuff, was anything getting through clearly. The AI was basically trying to read a detailed instruction manual with Vaseline smeared all over its glasses. So once you understand the problem with that much clarity, the solution becomes almost obvious, and it's incredibly elegant. That solution is Prism. Honestly, the best way to think about Prism is that it gives the AI a brand new pair of bifocal glasses. Instead of trying to force everything through one blurry, broken lens, it creates two separate, crystal clear channels so it can process both types of signals at the same time. And it works in three pretty simple steps. First, it pulls apart the high-frequency and low-frequency signals. Second, it processes them in parallel, on their own tracks, so they stop messing with each other. And finally, and this is the really genius part, it recalibrates and boosts that weakened high-frequency signal before putting them back together. The result? The AI gets a perfectly clear, complete picture of the text. So yeah, the theory is brilliant. But what about the real-world results? Well, this is where things get genuinely exciting. Let's start with the headline number, 5.1 times faster. Prism is over 5 times faster than standard full-fat attention when you're working with really long documents. That's not just an improvement, that is a massive, massive leap forward. And this isn't in a vacuum either. When you stack it up against other top-of-the-line methods, Prism is just in a completely different league. At a long context window of 128,000 tokens, it absolutely leaves its competitors in the dust. But here it is, the most important slide of all. You're probably thinking, okay, it's fast, but is it accurate? And the answer is a resounding yes. Look at this table. It compares Prism to full attention on a Llama 3 model. The average scores, they're practically identical. It gets that insane speed up with almost zero loss in performance. It's the best of both worlds. And this isn't some one-trick pony that only works for reading books. The paper shows that Prism's approach is super versatile. It delivers huge gains in understanding everything from complex code to finding tiny facts in huge documents and even, get this, analyzing hour-long videos. So, all of this brings us to one final huge question. For years, in AI, we've had to make a trade-off. You could have speed or you could have depth. You couldn't have both. Prism suggests that maybe, just maybe, we don't have to make that choice anymore. So the real question is, what becomes possible when our AIs can finally read and watch and understand everything we can, but in the blink of an eye?
All right, today we are diving into some research that might just flip the entire script on how we build artificial intelligence. It's called Opus, and it's all about training AI with better data, not just more data.
So, what if I told you an AI could get smarter by using less data? I know it sounds totally backward, right? For years, the whole playbook in AI has been more data, more power. But what if the secret sauce isn't about having more data, but about having the right data?
Now, to really get why this is such a big deal, we need to talk about this massive problem that's staring the entire AI industry right in the face. And that problem is something called the data wall. The simplest way to put it is, we're running out of good stuff to read on the internet. Seriously, these huge language models are incredibly hungry, and we've basically fed them the entire public web. But that well, it is absolutely starting to run dry.
And look, this isn't some problem for the distant future. Researchers are projecting that we could completely run out of high-quality public text by 2026, maybe 2028. That's really soon. So the takeaway here is pretty clear. Just throwing more and more data at the problem isn't going to work anymore. We need a totally new game plan.
Okay, so before we get to the brilliant new solution, let's take a quick look at the old playbook. You know, how we used to do things, and why it wasn't quite working.
So you had two main approaches. On one hand, there was static selection. You could think of this like a generic one-size-fits-all diet plan. You pick your data once at the beginning, and that's it. Then you have dynamic selection, which is a bit smarter. This is more like having a trainer who adjusts the diet on the fly as you learn and progress. Sounds better, right? Well, it had a really big hidden flaw.
And that flaw has a name, the misalignment gap. Okay, so stick with me here. The issue is that these dynamic methods were using a pretty simple ruler to measure what data was useful. But the AI's actual learning engine, this complex thing called the optimizer, it has a totally different and way more complex metabolism. So there was this huge gap between what the simple method thought was good food and what the advanced optimizer actually needed to get stronger faster. And this picture just says it all, doesn't it? On the left, that's the old way. It's this long, winding, inefficient path to the goal. It's like taking all the back roads. But on the right, that's the path the optimizer actually wanted to take. Straight, direct, super efficient. That gap between the two, that's just a whole lot of wasted time, wasted compute power, and wasted data.
Which brings us to the breakthrough. This is where the researchers had one of those aha moments that just changes everything. They figured out a way to completely close that misalignment gap.
And the key insight is actually so elegant, so simple when you hear it. They said, instead of using some generic outside rule to pick the data, what if we just ask the AI's own training engine, the optimizer, what it needs to learn right now, at every single step? It's like going from a generic diet book to having a world-class nutritionist crafting a perfect meal plan for you in real time.
And this quote from the paper just nails it. A batch of data is only valuable if it helps the AI move in the right direction, based on its own specific geometry. It's not about finding good data in some abstract sense. It's about finding the perfect piece of data for this exact moment in training.
So that's the big idea. But how do you actually build a system that can do this? Well, let's meet the hero of this story, a new framework called Opus.
So Opus, and that stands for Optimizer-Induced Projected Utility Selection, which is a mouthful, is the system that puts this whole idea into practice. It's basically a dynamic data selection framework that acts like a hyper-intelligent personal trainer for the AI, scoring data based on exactly how useful it is to that specific optimizer at every single step of the way. And here's the four-step dance it does. First, it establishes a goal. It creates this small, high-quality proxy dataset that it wants to aim for. Think of it as the gold standard. Then, step 2. It scores all the potential data to see how well it aligns with that goal, always considering the optimizer's unique geometry. Step 3 is super important. It selects for diversity. It uses some smart sampling to pick the best data, but also makes sure it's not redundant, so the AI isn't just learning the same lesson over and over. And finally, step 4, train and repeat. The AI trains on that perfectly selected data, and the whole process starts again for the very next step. It's a constant adaptive loop.
And I just want to give a quick shout out here. This wasn't some solo project. This whole Opus framework came out of a huge collaboration between researchers from top-tier places like Shanghai Jiao Tong University, UW-Madison, UIUC, and Mila. Just a ton of brainpower went into this.
Okay, so the theory sounds amazing, right? But the real question is, does it actually work in practice? Let's look at the results because honestly, they are pretty staggering.
First off, let's talk about efficiency. We're talking about an 8 times reduction in computation. That is huge. It means you can get to the same level of performance using 8 times less processing power. That's a massive saving in time, energy, and money.
But get this, it's not just about being faster, it's actually better. Compared to just picking data randomly, Opus boosted the model's final accuracy by an average of 2.2%. So you're using way less compute, and you're ending up with a smarter, more accurate AI. It's a total win-win.
But this graph right here is the real mic drop moment. What you're seeing is performance plotted against how much data was used. All those other lines kind of bunched up at the bottom, those are all the other methods. And that single line soaring way above everything else, yeah, that's Opus. It's not even close. It's in a league of its own.
Let me put that into perspective for you. What this graph shows is that Opus helps an AI get better results with just 30 billion tokens than other methods do with 200 billion. That's just incredible. It's the ultimate proof of learning more from less.
So what does this all mean? Well, Opus is this huge step forward in solving that data wall problem we talked about. It proves that the future of AI isn't just about getting bigger and bigger. It's about getting smarter, more efficient. And that leaves us with a really big question, right? If we can teach AI to learn more from less, what else can we teach them? How do we guide them to be not just more powerful, but maybe a little more wise?
All right, let's talk about AI assistants, because they're about to get a serious upgrade. I mean, we're way past just asking for the weather. Imagine an AI that can actually use your apps for you. Yep, let's get into it. Seriously, just stop and think about that for a second. What if your AI assistant could really do stuff? Not just, spit back a search result or set a timer, but actually take action. Exactly. We're not talking about small stuff here. Imagine you just say, hey, find and book me a flight to London for next Tuesday. And then you just watch as your phone does it. It opens the app, types in the details, clicks through all the pages, and bam, booking confirmed. Well, that's the kind of future we're diving into today. And it's all thanks to a brand new AI model called UI Venus 1.5. The whole idea behind it is to create less of a digital talker and a whole lot more of a digital doer. So you might be wondering, why don't we have this already? It seems like a no-brainer, right? Well, it really boils down to a pretty big roadblock in how our current assistants are built. Okay, so on the left, you've got what assistants can do now. They're kind of stuck in their own little world, right? They can answer questions, play music, but that's about it. But on the right, that's the dream. That's what we wish they could do. We want them to use our apps, handle complicated jobs, and most importantly, understand what's on the screen, just like we do. That ability to actually see and interact with the screen, that's been the huge missing piece. And that is where a totally new kind of AI comes into the picture. It's built specifically to solve this problem, and it's called a GUI agent. So what the heck is a GUI agent? Well, here's the key. It doesn't need some special, complicated access to an app's code. Nope. It literally just looks at your screen, just like you do. It sees the buttons, it sees the text boxes, and it figures out where to click, type, and scroll to get the job done. It has to actually find the submit button or the search bar visually. In the world of AI, they call this grounding. Basically, its understanding is grounded in what it can physically see on the screen. And all this info, by the way, comes directly from the technical report published by Ant Group's Venus team. This is the paper where they introduce UI Venus 1.5 and break down exactly how they built this incredibly powerful new agent. Okay, so how on earth do you train an AI to do something so human? Well, the secret sauce here is this really clever three-part training process they came up with. It's what gives this AI such a deep, intuitive feel for how apps actually work. First up, mid-training. The model basically went to school. It studied this enormous library of 10 billion pieces of data from over 30 different app data sets. You can think of it like an AI intern that was forced to read every user manual and watch every tutorial on the planet to learn the basics. Then came the real test, online reinforcement learning. This is where it learned by doing. But here's the cool part. It only got a reward, a good grade if you will, if it completed the entire task successfully, not just for one correct click. This forces it to think strategically about the whole mission, not just the next step. And finally, model merging. They took 3 specialized AIs, one that was an expert at grounding, one for web apps, and one for mobile apps, and they merged them all into one unified super agent. So it's this combination of massive book smarts, strategic, real-world practice, and then bringing together a team of experts that makes it so powerful. Okay, that training process sounds super impressive, for sure. But here's the million-dollar question. Does it actually work? Is it really any better than the other models out there? So naturally, the team put it to the test. They basically set up a digital Olympics, pitting UI Venus 1.5 against all the other top AI agents on a series of really tough challenges, or what they call benchmarks. And wow, the results speak for themselves. In all these charts, you're looking for the blue lines and bars. That's our champion, UI Venus 1.5. And as you can see, it doesn't matter if the task is navigating a super complex app or that grounding skill we mentioned, actually understanding the screen. It is consistently crushing it. It's right at the top or very, very close. Let's zoom in on a huge one. On this test called the Android World Benchmark, which is a brutal test across a ton of different real Android apps, it hit a 77.6% success rate. That's not just good, that is a new state-of-the-art performance, the best we've seen so far. But is it just getting lucky with its clicks, or does it get what it's looking at? That's what a grounding test is all about. And here, it scored a 75% accuracy in pinpointing specific things on the screen. That proves it's not just blindly tapping, it's genuinely comprehending the visual layout. And just to really drive the point home, on another really tough test called ScreenSpot Pro, it still nailed nearly 70% accuracy. So the big takeaway from all these numbers is pretty clear. This isn't a one-trick pony. Its performance is solid, it's repeatable, and it's versatile across all sorts of different digital hoops you make it jump through. Okay, so state-of-the-art sounds fantastic in a lab. But what does all this power actually mean for you and me, like in our actual day-to-day lives? This is where things get really, really cool. The paper talks about it being able to handle all the stuff we do every day. Booking tickets on a travel app, buying something from an online store, even finding a specific recipe on a cooking site that matches exactly what you want. Basically, just think about any annoying multi-step thing you have to do in an app. The whole point of UI Venus 1.5 is that you can just give it one command and it'll take care of the rest. So this kind of technology is clearly starting to leave the research lab and head out into the real world. And that leaves us with a really fun question to chew on. Once you have an AI that can finally do things for you, what's the very first, most annoying, tedious task on your phone you're going to make it do? Welcome to the explainer. So let me ask you something. What if you could build an entire software product from scratch without a single human writing one line of code? It sounds like science fiction, right? Well, today we're diving into a radical experiment from a team at OpenAI that did exactly that. And honestly, it might just change software engineering as we know it. So let's just let that sink in for a second. The goal here wasn't just to use AI to help. No, the goal was to build and ship a real product with literally 0 lines of code written by a human. Every comma, every function, every single character had to come from an AI. And the results, they were pretty staggering. An AI agent running on a model called Codex pumped out roughly 1 million lines of code in just 5 months. And we're talking about the whole shebang, the app itself, all the tests, even the documentation, everything. Now get this, the team figured that to do all that work, it would have taken a normal team of engineers about 10 times as long. So this was done in 1/10 the time. That is an absolutely massive leap in speed. So you're probably picturing a huge team managing this whole thing, right? Well, the team that kicked this all off, it was just 3 engineers. Seriously, 3 people guiding an AI to build a 1,000,000-line product from a totally blank page. So that brings up some pretty big questions, doesn't it? How on earth did they manage this? What did they learn from trying something so out there? And really, what does this all mean for the future of building software? Let's get into it. All right, so the whole thing kicked off not with engineers planning out the foundation, but by pointing an AI agent at a completely empty code repository and basically saying, go, build it. And from day one, they had one golden rule, one that could not be broken. Humans do not write code, period. Every single change, whether it was a tiny config tweak or a massive new feature, had to be generated by the AI agent. So, if you're an engineer and you're not allowed to write code, what exactly do you do all day? Well, this whole experiment completely flipped the job description on its head. It stopped being about typing syntax. Instead of getting into the weeds of writing code, the engineer's new job was to enable the agent. They became more like architects. Their focus shifted to designing the playing field, clearly defining the goals, and building really smart feedback loops to keep the agent on the right track. I love this quote because it just nails the new relationship. Humans are the strategists, the ones holding the map and steering the ship. The AI agents, they're the engine room, executing the complex, line-by-line work at a speed no human could ever match. Okay, but to make this all work, the team had to crack a huge problem in AI: context. How do you give an agent all the information it needs to do a complex job without completely overwhelming it? You know, their first try was exactly what you might expect. They basically gave the agent a giant 1,000-page instruction manual with everything in it. And it was a complete disaster. The info got outdated immediately, the agent had no idea what was actually important, and it just drowned out the specific instructions for the task at hand. So they pivoted to a much, much smarter approach. They started treating the main instruction file like a map or a table of contents. It was short, simple, and just pointed the agent to a well-organized library of documents. That way, the agent could just look up the specific piece of knowledge it needed exactly when it needed it. And this idea led to a core principle they call agent legibility. The idea is simple. The entire system has to be designed so that the AI can understand the project's goals just by reading the repository. All the crucial knowledge has to live in the code, where it can be tracked, not trapped in someone's head or lost in a random chat message. Now, letting an AI write code this fast sounds like a recipe for absolute chaos, right? To stop the project from turning into a mess, the team knew that incredible speed demands incredibly strong guardrails. So to keep things in order, they created these automated rules they called, and I love this name, taste invariants. You can think of them as a super opinionated robot code reviewer that works 24/7. It automatically enforces all the project style guides and design principles, making sure every piece of AI code is clean and consistent. And this was the blueprint for those rules. They built a really rigid structure with a strict one-way flow of data. See, information can only travel down this list, from one layer to the next. This prevents the tangled spaghetti code that slows so many projects down. It was this strictness that allowed them to move so fast without everything falling apart. So what happens when you put all of this together? You've got an agent that can find the context it needs, and you have strong architectural guardrails keeping it on track. Well, the agent's ability to just work on its own hit a whole new level. It could now take a simple bug report and handle the entire fix from start to finish. I mean, it would find the bug, write the code to fix it, test it, and then package it all up for a final review. The only time it needed a human was when it needed a real judgment call that only a person could make.
Okay, I know what you're thinking. An AI writing a million lines of code, doesn't that just create a giant, unmanageable pile of technical debt? A bunch of AI slop that humans will have to clean up later? It's a really fair question.
And the team's solution for this was just elegant. They automated the cleanup. They created an AI-powered garbage collection process. It's basically an army of little AI agents that constantly scan the code. When they find something that isn't up to snuff, they automatically open up a request to refactor and clean up the code. The AI pays down its own technical debt. When you boil it all down, this experiment shows that the future of software isn't about replacing humans. Not at all. It's about elevating our work. The hardest, most valuable problems aren't about writing code anymore. They're about designing the environments and the systems that allow these powerful agents to do their best work.
And that leaves us with a pretty powerful question to chew on. When the AI is handling the tedious, line-by-line work of writing code, what new, ambitious, world-changing ideas will you finally have the time to build? Because that's the future this agent-first world is starting to make possible.